Hi everyone, here I'm going to give instructions on practice for Unit 2, creating and coding matrix equation. So as I mentioned in previous lecture, to construct a matrix equation, the most difficult part is about the transform matrix, the matrix A matrix. So here I'm repeating the meaning of each row and column of the A matrix. So the ith column of the A matrix summarizes all the fluxes that transport out of the ith carbon pool. And the ith row of the A matrix summarizes all the fluxes transferred into the ith carbon pool. After you understand those concepts, it might be easier for you to do a practice. To double check you get things right, if you apply the matrix calculation rule and expand the matrix equation by row, you should get the exact carbon balance equation for each of the carbon pools. So for next practice, you have write down a carbon balance equation from the carbon flow diagram of the Century model. For today's practice, the first task is to write down the matrix equation from the carbon balance equations you got yesterday. You can use your own notations, or you can use the carbon balance equation I provided here is a very general one. In the second task, we are going to code the matrix equation of TICO model in Python. You have got very familiar with the matrix equation in a differential form. So by dx, we can numerically write dx as x at the current time step minus x at the previous time step, which gives us a way to calculate x at the previous time step from the carbon pool size at the previous time step. So if we give an initial condition, we create x0, and we know B, I, A, K, each of the matrix items at each time step, we could be able to calculate x1. After we know x1, we could be able to calculate x2 and then x3, x4, etc. That is how we track the carbon dynamics through time. In this practice, we are going to use Cabal Train. So the first step is to make sure you could run the Cabal Train in its default mode for Unit 2. To do it, click on the Unit menu, select Unit 2, click on the Exercises menu, select Exercise 2, and also specify the output directory, that is the path in which you would like to hold the model output, and click on Run Exercises. After you click on the Run Exercises, now will be a note pop up. It says the task has already submitted, and wait for a little bit. You should receive another pop-up notice after a while. It tells you that the simulation has already finished. Then go to your output directory. If you are successful, you should be able to see two files. One is the result PNG, a second one is output CSV. So for the result PNG, the figure shows the change of the carbon pool size for each of the carbon pool through time. And the CSV file basically has the similar information. In the second step, let's step into the default source code. The default source code is based on this TICO model. I provide the matrix form here in case you want to have a look. To see the source code, click on this menu, Edit Source Code. You should be able to see the source code in black and white. Here I'm showing a color highlighted source code. This source code can be generally divided into 4 parts. The first part, load Python packages and environment. The second part, construct the matrices and assign values to each of these matrices. And also specifying the simulation length. Here, n year equals 10,000. That means we simulate an ecosystem for 10,000 years. This EV list is the initial carbon pool size. That's our starting point. Here, the K matrix is our turnover matrix. This A matrix is the transfer matrix. This B is the allocation. The third part is the core part of this code. Normally, we need to do model simulation iteratively to calculate x at time n from x at time n-1. Here, you don't need to worry about this iterative process. The function general model takes care of all of those iterations. So basically, you only need to specify the simulation length, the initial condition, the external input rate, and also those matrices. This function will give you the result. The first part of the code basically plot the result and write the result into CSV. After you understand what the code does, you could start to change and play with the code. To change the code, click on Edit Source Code. Change one value in part 2 of this code. Save the source code before you click on Run Exercises. After you run the exercises successfully, you could go to compare the new results with the one before you change the code. 2 notes here. It's good to rename the output file in your output directory before you submit the new simulation. If you don't rename the files, the new file generated in the new simulation will overwrite the old ones. And the second note, it's good to take a note or remember what you have changed in your code and change it back after your exploration. You are free to explore on your own to understand what controls the system dynamics or any particular process you are interested in. It can be the input rate, it can be the turnover rate, it can be the transfer or location, etc. Here is an example in the top panels. I have a simulation of 10,000 years. As you can see, those poles didn't change with time at the end of the simulation. That is, they are getting into steady state. Well, the bottom panel is a simulation with 100 years. As you can see, we don't have enough time to bring the soil passive organic carbon, the slow soil carbon, etc. into steady state. They are still changed with time. In my second exploration, I'm interested in if I have a faster turnover of passive soil organic carbon, what does it mean to our system? So I changed the turnover rate of the passive organic carbon from a smaller value to a larger value. As you can see, my passive soil organic carbon pool gets into steady state quicker than the previous one, but the steady state value is smaller than the previous one. So feel free to do your own exploration. It's a way to help us to understand what and how different factors and processes control the system dynamics. So after you finish your own exploration, feel free to do the step 4, write and run a new matrix carbon model. This time we have a model with 7 carbon pools. The first carbon pool is leaf, second is root, third wood, metabolic nature, structure nature, fast soil organic matter, and passive soil organic matter. We have some of the external carbon input that is allocated to leaf, another fraction to root, and the remaining fraction goes to wood specified by this allocation matrix. Here is the transfer matrix and turnover matrix. Please go to modifying the part 2 of the code, adapt it for this carbon model, and also check the book practice 2 for the specific values of those matrix items. Again, please go to the Slack for help if you have any difficulties, and enjoy the practice.